Good morning, everyone. Today, I will discuss about nucleophilic substitution reactions. In previous lecture, we have discussed about nucleophile and electrophile, what kind of species can act as nucleophile and electrophile. So here, first of all, what is the meaning of substitution? Substitution means displacement. And the first is nucleophile. So in this reaction, nucleophile is replacing another group. That another group will act as leaving group. So nucleophile should be more stronger than the leaving group so that nucleophile can attack on that particular group. Let's understand the concept of nucleophilic substitution reaction with the help of example. In this case, methyl bromide, it is our first substrate, and the second one is aqueous QH. If we will talk about methyl bromide, here bromine is the electronegative element, so it will pull the shared pair of electron towards itself, so it will acquire partial negative charge, and methyl group will acquire partial positive charge. QH, we are using term here aqueous. Aqueous means it is made in water, so here it is present in the form of ions, K positive and OH negative. So you can see on the product side what is happening. This bromine group is replaced by the OH group. So this is a kind of nucleophilic substitution reactions. This is our byproduct. What kind of mechanism it is following? This OH negative will attack on methyl group acquiring partial positive charge, and this Br group will be expelled from here as Br negative. Br negative, and there is a formation of methanol. So it is very clear from this example. Bromine has occupied, hydroxide group has occupied the space of bromine. So OH negative here is acting as nucleophile. So this is very clear from this example what are nucleophilic substitution reaction. So we will discuss this in detail, as in nucleophilic substitution reactions there are two type of mechanism. One is SN2 and another one is SN1. So here what is the meaning of SN1 and SN2 we will understand with the help of examples. So first of all, we will try some more reaction with by changing this substrate alkyl halide with aqueous QH. Let's see another example. See, this is our primary alkyl halide. It is subjected to react with aqueous QH, and what kind of product in this form? In this again the alcohol is formed. Here bromine is replaced with OH negative group. So this is our product, but the alkyl halide we are here using is that is primary. Primary means when it is further attached to one alkyl group, and this is our functional group bromine. So here what kind of alcohol we are getting? We are also getting primary alcohol. So this is our one of example. So it follows SN2 mechanism. It follows SN2 mechanism. How it follows SN2 mechanism and why we will discuss in this lecture, but moving to another example. Yes. So here I am taking another example. In this alkyl bromide, I am taking that is secondary. You can see this carbon is attached to further two methyl groups. So I am naming it as secondary bromide. So it was subjected to react with aqueous QH under same condition, and the product we are getting is secondary alcohol. It can follow both It can follow SN2 mechanism as well as SN1. Here we are taking tertiary alkyl halide. In this, carbon is attached to 3 alkyl groups. So this is tertiary alkyl bromide. You can either say butyl bromide, tertiary butyl bromide. This is also subjected to undergo reaction with aqueous QH under same conditions. So it is forming tertiary alcohol. So, but it follows SN1 mechanism. So I told you primary alkyl halide. It follows SN2 mechanism. Secondary alkyl halide. It may either use SN2 or SN1. But tertiary alkyl halide, it follows SN1 mechanism. So what are these mechanisms, SN1, SN2? Now we will discuss these mechanisms. So basic concept was nucleophile will attack and the leaving group will be expelled from the substrate and there is formation of product. Let's see. SN1. So what is the meaning of SN1? Here S is capital and N here is used as subscript like this. And 1 is capital. S means substitution, N means nucleophilic, and 1 means first order. We can also call it unimolecular, nucleophilic, substitution, reaction. SN2, this is substitution, nucleophilic, second order. So it is also called as bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. So let's start with SN2. And we will start with SN2. See, SN2. In this mechanism, the rate of reaction depends upon two reactant. So what is the meaning of two reactant? As in previous example, we have been, let us we are taking ethyl bromide, its reaction with aqueous QH. So these are two reactants. One is alkyl halide, another one is aqueous QH. So in bimolecular nucleophilic substitution reaction, the rate of reaction will depends upon the concentration of both of these reactants. How? Rate of reaction is equal to K concentration of ethyl bromide and concentration of QH. If the concentration of both of these reactants is unity, then the rate of reaction will also be 2. If I double the concentration of ethyl bromide and also the concentration of potassium hydroxide, then the rate of reaction will become 4 times. If the concentration of ethyl bromide we are taking is 2 times and the concentration of hydroxide is increasing by 3 times, then the rate of reaction will become 6 times. So how the product will get formed, it is explained by the rate of reaction. How easily, how fast here product is formed, it depends on the rate of reaction. More the rate of the reaction, more is the formation of the product. So it depends basically upon the concentration of reactant. So here the rate of reaction depends upon two reactant. So this is very fast reaction. It occurs in only one step. And In this mechanism, there is also formation of an unstable product that is known as transition state, which will once formed, it will be easily disappeared and will be converted into the product. See, here you can take methyl bromide. Yes. So this is our reactant, ethyl bromide. This is primary alkyl bromide. OH negative group is acting as nucleophile. You can see this is the structure of methyl bromide, ethyl bromide. It is tetrahedral in nature. You can see OH negative will attack from the negative, from the back side. And there is formation of unstable species that is known as transition state. This is a transition state. In this, carbon is forming 5 bonds, which is not possible for carbon. Carbon maximum can form 4 bonds. So the species, the here, it is very unstable. So that's why it is called as transition state. In this, OH negative is attacking from the back side. You can see here bonds are represented with dotted lines. Why it is showing bromine here is expelled and OH negative is coming. So one bond is will be broken up and one new bond will be formed. The new bond formed will be with the OH group and the bond formed with and the bond with bromine will be broken. See, the product formed here is, you can see in this there is inversion of geometry, as this is not a chiral carbon, this is a chiral carbon. So when you will use the chiral carbon, you will see there is inversion in geometry. What happened? What is the meaning of inversion of geometry? Means if you are taking the reactant in D form, then it will convert it into L form. If you are taking reactants as L form, and the product you will get will be D form. This is the product, and here is the reactant. Its geometry will be inverted. Why its geometry will be inverted? Because the in which side leaving group is present, always the nucleophile will be attacked from the opposite side. So this is represented in this mechanism. In this SN2 mechanism, the rate of reaction is depending upon the concentration of the both reactant ethyl bromide as well on the concentration of QH, as this whole mechanism is happening in single step. Okay, 2 here is we are using here because the rate of reaction is depending upon 2 reactants. Clear? So this was about the SN2 mechanism. Yeah. So previously we have written here rate of reaction upon depends upon 2 reactant, 1-step process, and transition state is formed. These all are the features of SN2 mechanism. So next is SN1 mechanism. What is happening in SN1 mechanism? In these reactions, the rate of reaction depends upon only one reactant. It is a 2-step process. In this, the intermediate formed is carbocation. So here we are using the term intermediate. It is little bit more stable than transition state. So what is the meaning of stability? Means it's life. So it can appear for more time as compared to transition state. Both of these intermediate as transition state disappear when these will converted into the product. But mm, the major difference is the intermediate has more lifetime as compared to transition state. It can stay for more time. Let's see how the reaction proceed via SN1 mechanism. In this, we are taking tertiary alkyl halide. Tertiary alkyl halide. Why tertiary alkyl halides undergo SN1 mechanism instead of SN2 mechanism? Because you can see OH negative is the nucleophile. It will attack from the back side. So here is the steric hindrance. So OH negative cannot approach this central carbon from back side. So it do not follow SN2 mechanism due to steric hindrance in substrate. It do not follow SN2 mechanism. Then it will follow SN1 mechanism. What happened in SN1 mechanism? First of all, leaving group will be expelled. This is our first step. In this, leaving group is expelled from substrate. Here our substrate is have tetrahedral geometry. What will happen here? Br negative is Br is expelled from here along with the electrons of carbon, along with the electrons of carbon. If carbon will lose its electron, then it will get positive charge on it. This is known as carbocation. Here it is the intermediate. See, the carbon have 6 valence electron in its valence shell. 1, 2, 3, 4, 5, 6. There are 6 electrons in its valence shell and the carbon acquires positive charge. So this thus it is the carbocation intermediate. And here the geometry of carbocation is trigonal planar. It is the angle is 120 degree and there was a 109.28 minute. So tetrahedral is converted into trigonal planar. Now what will happen? OH negative nucleophile will attack on this carbocation. It can attack from the back side as well as from the front side. Clear? So there is formation of product that is tertiary alcohol. As the nucleophile is attacking from both back side as well from front side. So it can form D form as well as form L form. Whether your product may be D, either D or L. D means dextrorotatory. L means levorotatory. Means which can rotate the light in left direction, and D means which will rotate the light in right direction, which are optical active in nature. You can see here bromine is on the right side. So if we will take a chiral compound either D form or in L form. So here the product will form D plus L. 50% will be D form and 50% will be L form. So when the both optical active molecules were found in equal ratio, then it is known as racemic mixture, means it contains both form, D form as well as L form. So here in this case, there is formation of the mixture of both product. So the product is known as racemic mixture. But in case of SN2, there is inversion of geometry. I will write it on the separate page. So this was a concept of SN1 mechanism. Here, first of all, what will happen? There is formation of intermediate, that is carbocation. In second step, the nucleophile will attack and form the final product. I will write here SN2. In this, there is inversion of geometry. And in SN1, there is formation of racemic mixture, and it occurs in one step, and it is a two-step mechanism. In this, transition state is formed. In this, intermediate is formed. Okay, so basically this is the difference between SN2 and SN1 mechanism. And of course, I have told about the rate of reaction on what kind of alkyl halides follow SN2 mechanism, primary and secondary follow SN2 mechanism, and secondary and tertiary follow SN1 mechanism. We are saying secondary, it may be either follow both SN2 or SN1. It can follow both mechanisms. So basically on what factor it depends. The reactant will follow SN1 mechanism or SN2 mechanism. There are so many kind of substrates. Here we have just discussed about the alkyl halides, which are primary, secondary, and tertiary in nature. So first reason was the steric hindrance. If the substrate is sterically hindered, then it will always follow the SN1 mechanism. If it is not sterically hindered, it will follow SN2 mechanism. See, okay, so there are some other examples of nucleophilic substitution reactions. In this, our substrate is acetyl chloride. This is acetyl chloride. This is its common name, and its IUPAC name is ethanol chloride. Ethanol chloride. Here, methyl iodide. As we know, iodine is a larger group and it is electronegative in nature. It will acquire partial negative charge. And methyl, it will acquire partial positive charge. So, methyl positive. Here, wait a second. This is the wrong example. Here, we are not taking methyl iodide. Yes. Here we will use the Grignard reagent as another substrate Mg. Yeah. So it acquires negative charge, the whole acquires positive charge. So here methyl will attack on this electrophilic center. We have discussed already why it is act as electrophilic center in our previous lecture, where we have discussed about electrophile and nucleophile. Here is the partial positive charge, partial negative charge. So what will happen when this methyl CH3 negative will attack? There will be electromagnetic shift in the electrons. Then these electrons will be shifted towards oxygen. See its mechanism. CH3, C, O negative, CH3, Cl. 1, 2, 3, 4, 5, 6. So I am representing its valence electrons. So in next step, what will be happen? This electron will be transferred again to the carbon and Cl will be expelled as Cl negative and the final product formed is CH3 CO CH3. Okay, so this is acetone. So this is a kind of nucleophilic substitution reaction. In this, chlorine is replaced with methyl group. When chlorine is present in the form of negative charge, then we call it as chloride. So here correct terminology is chloride is removed. So we are taking another example in which the substrate is ester. Okay, so same nucleophile we have been using Grignard reagent, methyl magnesium bromide. Here it is our nucleophile. So same methyl group will attack over this carbon and there will be electromagnetic shift and the electrons get back towards carbon and OCH3 group negative act as leaving group. So this here we can call OCH3 as methoxy. Methoxy anion will be expelled from here. OCH3 negative as leaving group. So this is also the kind of nucleophilic substitution reaction. As you can see in both of the case, the product form is same, but we are taking different reactants and the same nucleophile. So leaving group may be different. Leaving group may be different. Okay. So this is the example of carbonyl groups. Carbonyl groups also undergo nucleophilic substitution reactions. As previously we discussed alkyl bromides. So next, there are some other factors which affects SN1 and SN2 mechanism. Another one is the polarity of solvent. Polarity of solvent, what kind of solvent we have been using in particular reactions, if either we are using methanol, water, DMSO, DMF. So basically what is the difference between these of two solvents? Methanol, partial negative, partial positive, it can lose its proton, yeah, CH3O negative. It's a reversible reaction. Water, it can also lose its proton as H positive plus OH negative. H, wait a second. Here H positive. Okay, and OH negative. So these are called protic solvent. Protic, which can lose its proton, which have proton to lose. Polar, these are polar in nature because they have a particular dipole moment. Dipole moment always is from positive to negative, positive to negative. Clear? Dipole moment always have a direction. So these are polar in nature because their charges can be separated, can be polarized. Let's see in the case of polar or protic solvent. So These are also polar in nature because their charges can be separated. They have particular dipole moment, but these are aprotic in nature. What is the meaning of a? Aprotic means these cannot lose hydrogen. So these are two different categories of solvent, protic and aprotic solvent. One is polar protic, another one is polar aprotic solvent. Clear? So what kind of solvent we have been choosing, it affects what mechanism should be followed, whether S1 or SN2. We will discuss in next lecture. Second one is what kind of nucleophile we have been using, whether it is hard or soft. What is the nature of nucleophile? Such as OH negative. It is hard nucleophile. SH negative. It is soft nucleophile. So if it depends upon different nucleophiles, what kind of mechanism should be followed. This all will be discussed in the next lecture. So let's take some more examples of reactants or substrate which will follow SN1 or SN2 mechanism. Methyl X here is halide group. X is halide group. It may be chlorine, bromine, iodine, any of these. Okay. So SN2, yes, it will follow SN2 mechanism, which occur in one step in which there is no steric hindrance. Clear? This is primary alkyl halide group. Here we have used R group. It will also follow SN2 mechanism. Secondary alkyl halide. It can follow both. So I have ticked both of yes. Tertiary alkyl halide. It will follow only SN1. It do not follow SN2 mechanism. Again is alkyl halide. Okay. It is sterically hindered. So it do not undergo any of these substitution. Neither SN1 nor SN2 because it is completely sterically hindered and it is not stable. Clear? See next, electrophile. I will discuss why this is not stable in right now, but let's move to another substrate. Here, this is allyl halide. This is our allylic carbon. When a saturated carbon is attached to double bond in this manner, count the numbering 1, 2, 3. Then this third carbon is known as allylic carbon and this whole group is known as allyl group. So it is attached to the halogen, therefore it is known as allyl halide. It can undergo SN1 mechanism and SN2 mechanism. Let's see, first of all discuss about this allyl halide. Bromide. Okay. For SN1, there will be formation of intermediate SN1. In SN2, there is formation of a transition state BR. Here are H. H. OH negative will attack from backside, and there is formation of a transition state BR. Here is a solid bond. As we are showing here, the nucleophile is attacking, and OH, H. Okay. So this is transition form. If it will follow SN2 mechanism. In SN1, there will be formation of carbocation. Why it will follow SN1? Because this is not sterically hindered, but it can follow SN1 mechanism. You can see there is double bond at the adjacent position. So it can undergo resonance. It can undergo resonance. This pi electron can be shifted from this carbon to this carbon. I will number the carbons so that you can easily identify what is happening here. This is carbon number 1, 2, 3. So these pi electrons get shifted from carbon number 2 to carbon number 3. Here is the formation of double bond, and now it will be on first carbon. Positive charge will be on first carbon. You can see these both are resonance structures. See, so here positive charge is stabilized by this pi bond, which is from allyl group. So when there is stabilization of carbocation, then it can follow SN1 mechanism also. So there should be the stability in the carbocation. Clear? Then next examples. Same benzyl bromide. What is the structure of benzyl bromide? CH2. Yeah, this is the structure of benzyl bromide. So it is not sterically hindered. It can follow SN2 mechanism as well. It can follow SN1. Why it will follow SN1 mechanism? If the leaving group is removed as Br negative, then there will be positive charge on this carbon H. This group is known as benzylic group, benzyl bromide. So this is benzyl carbocation. You can see there are 3 pi bonds in benzene. These are in conjugation. So there can be mesomeric shift. These pi bonds can be transferred to another atom. So there is stabilization of this carbocation CH2, and the positive charge will come on this atom. Then there can be further movement of these pi electrons. Another resonating structure can be formed like this. CH2 double bond, and positive charge will be there, double bond. Same. One more transfer of pi electrons, that is also known as mesomeric shift. Now the positive charge will be on this carbon CH2. Then again there can be transference of electron, because these all are conjugated in nature. Conjugated means both, all of these are present at the adjacent position. So let me number these. Let me mark the numbering. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So in this you can see there is double bond between carbon number 1 and 2. In the first structures there is no double bond between carbon number 1 and 2. And in second structure there is the positive charge at the carbon number 3, and in third structure the positive charge is at carbon number 5, and in fourth structure the positive charge is at carbon number 7. Then again, the whole process is repeated. Again, we got the positive charge on the first carbon, that is benzylic carbocation. So in this case, the carbocation is stabilized. So thus it can follow SN1 mechanism also, because it do not contain any kind of steric hindrance, as we have already discussed one case which can follow SN1 mechanism. That was the in which the substrate is sterically hindered. But the substrate which can be resonance stabilized can also form SN1 mechanism. See another example, ether. Another example, we have been using group R O CH2 Cl. So this is basically the ether group. Yeah, it is partial negatively charged. It is partially positively charged. Here, there is no steric hindrance. Here the Cl is the negative group. It can act as, it will be expelled as Cl negative. So it will follow SN2 mechanism. But it cannot follow SN1 mechanism. Why it cannot follow SN1 mechanism? If this Cl negative will be removed first, what will happen? R O CH2. There will be the positive charge on this carbon group. Okay, as we know, oxygen is electronegative in nature. It will pull the shared pair of electron toward itself. It will make the electron, it will make this carbon more electron deficient. So we can say in other words, it will destabilize this carbocation intermediate. Always which intermediate is considered stable? The intermediate in which positive charge is nullified by negative charge, either negative charge or by the groups which donates electrons to the carbon which requires positive charge. So carbocation which can be nullified by negative charge, that is more stable. So here we can also see, as in previously we have discussed, tertiary alkyl halide, yeah, tertiary carbocation, secondary carbocation, primary carbocation. Yeah. If we see in which, if these follow SN1 mechanism, let us suppose these all are following SN1 mechanism, in which the rate of reaction is fast, in which there is tertiary carbocation. Okay, tertiary carbocation has more rate of reaction as compared to secondary carbocation. Why? Because tertiary carbocation is more stable. Why tertiary carbocation is considered more stable? Because of the inductive effect of these methyl groups. Inductive effect. So inductive effect is always of two types, plus I and minus I. Plus I, the groups which donates, या फिर you can use the term releases electrons, show plus I effect. So here methyl group is showing plus I effect. It releases its sigma electrons towards this carbon. There are three methyl groups which are releasing their electrons towards this carbon carrying positive charge. So these are nullifying this positive charge. But in case of secondary, there are only two methyl groups which are releasing their electron towards this carbon carrying positive charge. So therefore, tertiary carbocation is more stable than the secondary carbocation. There was another factor apart from inductive effect, that is hyperconjugation. In hyperconjugation, what happens? Positive charge. This carbon hydrogen will bond will be broken, and this bond will participate in hyperconjugation like this. It will donate its sigma electrons, positive H H CH3. So by this, hyperconjugation can also stabilize the tertiary carbocations. Okay. 1, 2, 3, 4. Okay. So there will be no positive charge on this carbon. Wait a second. Hmm. There will be positive charge on the hydrogen. So hydrogen will give its electron to this carbon, and this electron will remain here. I will use different marker to represent the electron. Electron 1, electron 2. So this hydrogen will give its electron to carbon number 2. So there will be formation of a pi bond, and the H will get positive charge. So there is no bond between carbon and hydrogen. It is also called known as no bond formation. So hyperconjugation also stabilizes this carbocation. Let's see, in case of tertiary carbon, there are 3 hydrogens over there, 3, 6, 9. So 9 alpha hydrogens, which can stabilize this carbocations. More the number of structures, hyperconjugative structures, more is the stability. As this is our first hydrogen, second hydrogen, third hydrogen. All of these hydrogens can participate to give a hyperconjugative structure. Similarly, another methyl groups can also participate, so it will form 9 hyperconjugative structures because it have 9 alpha hydrogen. But in case of secondary carbocation, there are only 6 hydrogens, so it will form 6 hyperconjugative structures. So that's why tertiary is more stable than secondary. If we compare the rate of reaction, which is more, in which case it can easily form the product. In case of tertiary, it will get easily. Thus the product formed in tertiary carbocation is more easily and more effectively. Let's discuss another example. The last one is RCO CH2Cl. Okay, so this is the example of ketone. This is ketone group, and in this, the Cl is the leaving group. So what is happening here? It is also following SN2 mechanism. You can see it is following SN2 instead of SN1. The same is true. Let me explain with example. It is following SN2 mechanism. If it undergoes through SN1 mechanism, we are just supposing what will happen. CH2, there will be the positive charge on this carbon, as we know. Carbonyl group. Carbonyl group is, if it pulls electron, how this is the oxygen. There is electromagnetic shift, O negative and positive charge, R group, CH2 positive. So this is not possible. This carbon cannot pull the electrons from this CH2. It do not provide the electrons to this CH2 positive group. So it destabilizes the molecule. Thus, it do not follow SN1 mechanism. It only follows SN2 mechanism. The another last one was yeah. So we are done with all the examples. So I have told you what kind of molecule will follow SN1 and SN2 mechanism. Here, it depends upon the substrate, solvent, polar protic or polar aprotic. Here, plus substrate, solvent, and hardness or softness of nucleophile. So these are the factors which affect the SN1 and SN2 mechanism. We just have done with our part substrate. So what kind of substrate can undergo SN1 and SN2, and the effect of solvent and the nucleophile, we will discuss it in the next lecture. You can see as in SN1, the rate of reaction depends only on one reactant, not on the nucleophile. So in this reaction, the nature of nucleophile do not affect the mechanism. So it depends on the substrate plus solvent. In SN2, it depends on solvent, substrate plus solvent plus the nature of nucleophiles. So here are the three factors. Here are the only two factors. We have already discussed about SN1 and SN2. So it all was about the nucleophilic substitution reactions. If you have any kind of queries, you can comment in the comment box and I will answer you. So thank you. In the next lecture, I will discuss about the solvent effect and the effect of nucleophile on SN1 and SN2 mechanism. Thank you.